Good afternoon, ladies and gentlemen, here in New York City. Good morning, good afternoon, good evening if you're following this next general session out there on the World Wide Web via SYS-CON TV. We have Duke Skarda up next, long-term supporter of Cloud Expo. What is his company? The much talked about and newly acquired SoftLayer. Let's give it up, please, for Duke Skarda, CTO of SoftLayer. Enjoy.
Thank you. All right. Good afternoon. Thank you, Jeremy. Words give a good voice to concepts. Without words to a concept, the concept of just about anything can quickly fade. Over the years, we've done a lot of talking. There's been a lot of words given to cloud computing, cloud architecture, all the various products that we've developed for cloud. But we don't often talk about the concepts behind it. And we make it difficult, I think, a lot of times for customers to map what they're doing into the cloud. We've given customers oftentimes one concept, which is just cloud. So what I want to do today is give a much broader language to the concepts behind cloud and really talk about how to leverage it to the most benefit for your application. I want to kick it off by thinking a little bit about wine, which is always a nice thing to think about. When you have your first glass of wine, go back to whenever that was, it's kind of difficult to explain what your first sensation is, right? You either liked it or you didn't. You're not real sure how to describe it. As you think about it, your response was typically one of either, I didn't like that. Maybe on your second glass of wine, you liked it a little bit more, and you came up with a new concept that, I like that one was good. You say, well, why did I like that one versus the other one? Very simple response, perhaps. It was sweeter. I like that. That tasted good. You didn't have much of a language to really describe it. As you kept drinking wine, and you had more and more, tried different flavors, tried different types of wine, you began to acquire a much better palate, right? And you began to think of, I like reds or I like whites, one or the other more. Within reds, you began to notice the difference of the reds. Your palette and your language got much more complex. You began to acquire much more descriptive language for how you think about wine. There's a lot of people in the world who can talk about wine extensively. I'm not really one of them, but they came up, there's a pretty broad language to talk about wine. You can talk about it in ways you would never have thought of regarding wine. It's austere and masculine, has notes of jam, has words like cassis. I don't even know what that is. There's a big descriptive language around wine. The wine industry has even begun to develop ways to standardize how you think of it. And these are all ways not intended to help the wine industry. Obviously it does because you buy more, but it also is there to help you as a consumer of wine. You get a big color wheel of words and a very good taxonomy of the various flavors of wine. But we don't really do this for computers a lot, for servers. We do this in lots of areas of our life. Lots of cultures have lots of different words to describe things you wouldn't think you need lots of words for. Many of you may have heard the Inuits supposedly have some like 50 words to describe snow. There's another culture that has like 70 words to describe ice floating in the sea. Ice that has holes like Swiss cheese has a name for it. Ice that's there year-round has a different name. All of these different taxonomies for things that seem fairly straightforward. There's even a group in like Northern Europe that has like 1,000 words for reindeer to talk about their different shapes and their fitness levels. But when you think of cloud computing, one of the more complex things we've invented, there's not a ton of words. You typically think of cloud. And a lot of people, whenever I start talking to our customers, they don't even really necessarily think of different types of cloud. They say, well, what are you comparing? What are you even talking about when you say, well, what kind of cloud do you want? A lot of the times the response is, isn't there just one type of cloud? Aren't there maybe two models, private and public cloud? What exactly are you talking about? So what I want to begin to do is put the first layer of our taxonomy today, 4 types of cloud. Really 3, with one with a major subdivision. You got public virtualized cloud, and we're going to define all these later. Public virtualized cloud, which is typically what most people think of as cloud. Public bare metal cloud, and then private cloud, which has 2 very big distinctive types. On-premise, which I can describe as either in a company's data center, a corporate data center, or in a co-location somewhere. That's really where the corporation controls all aspects of the prem. So on-premise cloud, hosted private cloud, versus a hosted private cloud where it's in someone else's data center. You can also, of course, have mix and match these. You can combine these for the architecture that you really need. So as we begin to expand our language, we're going to use that as our basis, those three types of cloud. Before we get deep into comparing those three things, I want to step back just a little bit and talk about how you get real value from cloud. Because unless you understand the drivers behind why you're even using cloud, you'll end up using it incorrectly and do things wrong. So we're going to go back a couple decades and think of a microwave. I don't exactly know when it was invented, maybe the 50s and 60s or something like that. Before the microwave, everyone cooked always on a stovetop, right? You had a fire of some kind and you were cooking with it. Well, microwave completely revolutionized that and made it so that you could cook, you could boil water in 2 minutes. You could cook, microwavable mac and cheese in 3 minutes. You can cook things very, very quickly. And I remember when I grew up in the 70s, the microwave, I just always assumed that in the future, that's all we would cook with. There wouldn't be anything else. But we all know in our kitchens today, the microwave is still there. It's not like we shoved it to the side and don't use it anymore. But as we began to understand the real value of the microwave, that its speed, it took its place in the kitchen, right? It's still there. It's a very important spot. In this picture, it's in the corner, right? A key part of the kitchen. But also in this picture is the old-fashioned stove with a stovetop and an oven inside of it. That stove probably has all kinds of cool things that didn't exist in the 50s, like infrared sensors and what. But, so things evolved. But the microwave didn't replace all kinds of cooking. It became one of the ways that we cook. So as you think of value that you get from something, cloud, a microwave, it's always a balance of things, right? In the case of compute things and things we do in the IT world, it's typically a balance of time and money. Are you going to throw money to get there quicker? Or are you going to save money and allow it to take a little bit longer? Oftentimes, those two are mutually exclusive. You can't get both cheaper and faster. One of the real values of cloud is that it's a new operations model, a completely new way of delivering compute that gives it to you very quickly, seemingly infinite, at a very reasonable cost. So for the first time, it begins to feel like maybe we do get both time and money improvements. But there is always a trade-off, and that trade-off, in the case of cloud, comes with a loss of control and a degree of transparency that you lose. As you gain the things like capacity on demand and paying for only what you need right now, you begin to lose a little bit of control. The provider has to gain his value somewhere and has to standardize things. You begin to lose a little bit of control and transparency. So the key in cloud is understanding how to maximize your value and find the right balance, get the right trade-offs that make sense for you. So understanding the models is key. Understanding the value that you get from cloud. Are you looking to save money? Are you looking to get there faster? Are you looking for a little of both? How does your application fit into that world? That's the key. Understanding how to leverage the strengths of these different types of cloud to get what you need for your application. So that's the first step in comparing the models, is really understanding where that value comes from and knowing what you're trying to get out of it. The second thing, now we can begin to get a little bit more technical, is you want to begin to think of the various bottlenecks that exist. There are, generally speaking, 3 key elements that have been used since the early 1900s when we started making computers. 3 key elements that make up a compute environment. The compute itself, the CPU, the server itself, storage, and the network that connects those things together. I'm going to break them into 2 groups, and we're going to talk about them separately. We're going to talk about local bottlenecks first, which is primarily the compute and its immediate storage stuff. Then we're going to talk about some of these global elements and the bottlenecks associated with them. The local elements, if we start with the compute, is really always starts with, the first thing you look at when you're buying a computer, a laptop, or a server. What kind of CPU is it? What speed does it have? How many cores does it have? We're going to think of that as power, as compute power. Second thing is, what is the type of CPU? And do you have special needs? Do you have a special architectural needs that drive you to one architecture of a CPU or another? There's a standard Intel CPU. You get GPUs now for graphical processing or for sort of mass high-performance processing. ARMs, do you need an older processor because you've got an app that uses something in an older processor? You need something newer? Do you just not care? You just need a processor. These are things to consider. The workload on the server. We're going to think of this sort of simplify this as your neighbors. What's happening on the server? Is it just you? Do you have full control over it? Or are there other people on there, maybe other processes that you also have, right? What are they competing for on that box? And then finally, the last thing that really impacts the server itself and the processing power and the speed of the process is data locality. Where is the data, and how long does it take to get into the processor? Because you can have great core speed, lots of cores, you can have great control over it, but if it takes a second for your data to get to you every time you go fetch a new piece of data, your application is probably going to crawl. Which brings us to the second key element when you think of designing your server. The second key local element is storage. And I'm going to call the local parts of storage as being performance related. The global stuff is more accessibility. When you think of performance and storage, the first thing to think about is how fast is it? Typically we just talk about IOPS. How many operations can you get out of that thing? How quickly can it get data? How quickly can it find it and get it back to you? So there's IOPS and there's the delivery time. And delivery time is impacted by a couple things. Locality, as I just mentioned. Is it in the box? What kind of backplane do you have inside that server? What kind of RAID controller do you have in that server? All of those things are very important to how the disks within the server operate. Do you even know if your storage is local or is it remote? Once you begin to put it out on the other side of a network, you begin to have consistency issues. So now this is the third element of storage performance I want you to think about. What kind of consistency and control over the consistency do you have? This again comes down to neighbors. It's mostly neighbors in the network and other neighbors that are sharing that storage platform with you if you're accessing from a NAS or a SAN. When there's no one else on that storage network, you're probably going to get fantastic performance. When there's a lot of other customers beating up on the same storage drives and the same storage network, your performance may go down. How important is this to you? That's a key thing for you to consider. So we're going to call that neighbors when we think of storage performance. And then finally is how much size is available to you? How quickly can you scale that thing? So as you think about these two sets of local elements, things that you need to think about when you're thinking about when you're designing your cloud servers, those are the things to consider. Let me give an example of how these things come together. Two fairly well-known products. Oracle, been around forever. Don't need to describe that. It's a big relational database system. Been around for decades. And over the years, it's been highly tuned. There's a whole army of people out there that know how to tune Oracle very well. And it's generally tuned to scale vertically. Great big servers, lots of memory, with storage that's off-board. You have one, maybe two servers in a rack cluster. If you're really, really good, you can get a third one off-site somewhere. But that's very complex, takes a lot of engineering to make all of that work. But it's built to scale vertically. There's nothing wrong with scaling vertically, you just need to know that that's how an Oracle box scales. When you're using some of the new NoSQL servers or big data servers, they innately scale horizontally. In the example here, we're calling out Cloud, one of our good partners. Cloud's a document-oriented database, and it scales natively horizontally. It's made to work with local disk. It wants quick access times. It wants lots of servers. They communicate with each other very well. It knows where it puts everything, and it works across data center boundaries very, very well. The way you're going to design an Oracle box is very different from the way you would design a Cloud box. You want big servers versus lots of little servers. So these local elements, when you're thinking about cloud, are very important. So you don't just want to grab a cloud box off the shelf and say, I'm going to use this for everything. You want to think through, what do I want from my cloud server? How is it going to best map to what I'm trying to do with it, and how do I get the most performance out of it so I meet my value goals? The third thing we want to talk about are these global bottlenecks, which I mentioned a moment ago. Same three elements: compute, which is very local; storage, which has sort of a local element to it and a global element; and then the network, which is very clearly a global thing. So let's look through these global elements. Let's finish off with storage. When you think about the accessibility components of storage, now you're really trying to understand how are various servers in your application infrastructure going to get into your storage box. Are they reachable globally? Is it reachable privately, or are you going to go over the public internet to get there? Second thing is, what kind of redundancy is innately available to you? We're going to think about this as sort of your recoverable options. If you have a problem, are you going to be able to recover your data in that same data center, in a remote data center? What kind of redundancy options do you have? And then second to redundancy and recoverable is, how quickly can you recover? Do you have good failover built in to your storage options? When you have an outage on one disk drive, is that going to bring your entire infrastructure down, or do you have the ability to instantly be using other disk drives? You know, RAID controllers, there's a lot of different ways to go about this, but you want to consider that aspect of storage. And then finally, is content caching. What kind of caching options do you have both in the server and at your ends of your network, so that your various server components, application elements can get access to the data quickly, even in remote sites? So do you have various content caching available to you? Which brings us to network. That's very tightly related to your network. When you're thinking about the network for your cloud computing environment, you want to think about what kind of throughput and efficiency you have there. Those are the two parts of speed. When you think of speed, it's, you know, how big is the pipe and how efficiently is that pipe laid out? Are you going to take a dozen hops to get from server A to server B in the same data center? When you go from data center A to data center C, are you going to go over the public internet, or are you going through a private backbone? You know, what efficiency do you have in your network, your global network? Which brings you to a consistency question. What consistency constraints do you have? Does your application need to have a fairly tight, does it need a very tight sense of latency? Always 50 milliseconds from this box to that box. Those are going to be okay with every now and then it goes up to half a second to get from one box to another. So you need to understand your consistency concerns, but you know, typically that's thought of as jitter in the telecom world. Reliability. What kind of multipath options do you have in and out of your server and in and out of the data center? And then connectivity for one data center to another, for the data center to your customers. How do your customers get onto the network that your server is on? How quickly do they get on there into a private environment? How many peers do you have? Can you access from your server? All of these things have a great impact on your network throughput, your network speed, and the way you design your application. Typically, though, most people just think of cloud as that one glass of white wine. It's good or it's bad. But there are tons of options and a lot of ways for you to develop your own architecture using all the different elements that exist out in the public. So let me give an example here of how these global options can come to play in two different environments that are very easy to imagine. The first, we're going to think of enterprise applications. Maybe this is an enterprise ERP platform. In the enterprise, you're going to have a fairly defined user base. You're going to know how many of them there are. You're going to know where they are. They're fairly predictable when they come to work. You know, they're going to be there from 8 to 10, and you got 24/7 workloads. You know pretty much how that stuff is going to work. And this is a cost environment. This is an environment where it's a cost center. On the other hand, you can think of an internet application. Perhaps you're building and rolling out, you know, an Instagram competitor or something like that. In that world, you have a fairly global potential. You're hoping for global potential. You hope it's not just in your one area that your application's a big hit. You hope that you have lots of customers. And when you begin to get global customers, you don't really know when they're going to come online. You can't predict when they're going to sign up for your service. So you may have scale that goes up very, very quickly. You may have different needs throughout the day and night. Maybe everyone's on at from 2 to 5 in the afternoon while they're surfing at the end of the day at work, or they're on, at midnight at home while they're playing an online game. Their workloads can be very unpredictable in this world. And in the internet application world, you're on the revenue side of the ledger. So the way you're going to go about buying cloud in both of these instances should be fairly different. In the top, in the internet application world, you're going to be thinking about cost, efficiency. You're thinking about a specific set of locations, and you're not really going to need to scale up instantly. The ability to spin up a new VM in 2 minutes really isn't important in running your ERP application inside the enterprise. On the internet app, on the other hand, you want to have lots of data centers. You want to be able to have your application get as close as possible to the customer, lots of locations, to focus on performance. And you may need that ability to scale up very quickly. Those are two very different sets of requirements for what you're looking for in your cloud. So that's how to map those global elements to cloud. And there's a bunch of other stuff we're not going to really talk about, but these are all equally important. I'm going to mention complexity in a little while because it's important, but we're not going to go into a ton of detail. But obviously there's other things like your operating system and the software that you're writing and the software you're running. All of those things play into your environment, but they're not really based too much on the cloud. Those are choices that you can make. So finally, let's actually compare the models now. Just to remind you, we've got 3 models we're going to look at. We're going to bifurcate the private clouds into hosted and on-premise. And here's the definitions we're going to use for these. We're going to think of tenancy. First and foremost, I think, defines how these things work. In a public virtualized cloud, which is what most of you think of as cloud, it's a multi-tenant compute environment and a multi-tenant network. You've got other neighbors with you. You might be able to pay a premium and not have a neighbor with you, but by and large, it's a multi-tenant environment both at the compute, at the server layer, and at the network layer. Moving on to bare metal and a private hosted cloud. That's a single tenant server. It's only you on that box, and you have multiple tenants with you on the network. On the far end, you can get a private on-premise cloud. Now you're single everywhere, right? It's only your corporation that's in that cloud. You think of the controls. These are some of the trade-offs that I talked about earlier. When you get to a public virtualized cloud, you really have no design control over how that server is built, what storage architecture it has, how it's put together, how it lives on the network. You have minimal to no controls over that. On the bare metal, you've got a lot of controls now because you're building the box. At a private hosted cloud and on-premise cloud, you got complete control of those things. The runtime controls, in a public virtualized cloud, you control your VM. In a public bare metal cloud, you've got host control. In a private hosted cloud, you can manage the cloud any way you want. And in a private on-premise cloud, you have complete control over every aspect of it. Finally, consistency of performance in these environments, of your experience. In a public virtualized cloud, this is where we begin to get a little more negative on a public virtual. You have an inconsistent experience at times. As you get to a box where it's solely managed by you, you can control that experience more, so you have medium or high level of consistency depending on how good your management is over that box. But you at least have the control to do it. Your ability to scale and the starting costs, though, of the public cloud are great, right? Scale instantly, very low starting costs. At the opposite extreme, an on-premise private cloud, your weeks, maybe months, it's whatever your purchasing cycle and your planning cycle and your data center space acquisition cycle, that's going to define your ability to scale on a private on-premise cloud. And very high starting costs, right? You've got to buy a lot of stuff to get going. So those are kind of your spectrums, definitions of these 4 types of cloud compute. Now, as we map our performance attributes onto these types, we're going to first look at these local performance elements. At the compute level, the power, you have variable power in a public virtualized cloud. It's selectable. You can select exactly what you want in a bare metal or a private hosted cloud, and you can customize it to your heart's consent in a private cloud, an on-premise cloud. You can buy whatever you want. You can mix and match. In those hosted environments, you have to take what the service provider has for you, which is typically a pretty good array, but you can select exactly what you want from that. Specialty architectures, not really available typically in a public virtualized cloud. There may be a couple, but by and large, it's get what we're going to get what we give you. Neighbors, public virtualized cloud, obviously you have neighbors. These others are private environments, so you don't have neighbors, at least on the server itself, on the compute box. Fetch time is controllable in those environments where you're defining your cloud, where you're defining your architecture. You don't really have any control over that in a virtualized cloud. You can test it, you can know what it is, but you don't have much control over it. So that's how compute maps into those 4 types of cloud. Let's look at storage. Storage speed in a public virtualized cloud, again, is variable. You don't have a lot of control over it. It's controllable through your architectural skills in these various private environments. It's more controllable, obviously, in an on-premise environment, but it's still controllable in the bare metal environments as well. And your consistency is going to map to how much control you have. The local stuff is controlled by the compute model you select. If we look at global performance, there's the storage stuff that we talked about is about looking at the provider. What does your provider give you in the way of shareable storage, in the way of recovery options? How much of it do they provide you versus what do you need to create? What products do they give you for distributed caching? At the network level, do they have a private environment, a private network for your servers to live within? Are there multiple paths? Look into these elements of the service provider. Global performance is really more dictated by the service provider and their network and their data center layouts. So let's go to a quick test case, and we're going to look at actual performance numbers. We're going to bang through these. There's a lot of slides for just a couple of minutes. We're first going to look at MongoDB. So these are tests that we've performed. We've got an engineer who's done lots and lots of these, and you can read all the details. We don't have a lot of time here to go into a ton of details. But here's the basic idea. We're going to go through a small and a medium-sized test with MongoDB. The first one is what we call a small environment, single proc, 4 compute units, about 8 gig of memory in each of those, 200 iterations of 6 queries to 1 update. And you can see how it scales. Those are clients on the horizontal axis and operations per second. This is the public cloud. You can see it that's fine. There's not a huge problem here. It goes up to about 835 ops per second. In the bare metal cloud, you can get that up to 835. So that's nice. And these are, like I say, about the same configuration and roughly the same cost by the time you add everything into it. You look at the medium test. Now we're talking a dual 6-core box, 26 compute units, starting to get a little more expensive, 30 gig of memory. Same kind of test. In the public cloud, in this medium-sized environment, you get up to about 1,600 ops per second. You can see it begins to flatline a little bit there. But when you get to the bare metal, that flatline doesn't take effect. You've been able to design the box now. It's much more readily available. It's very custom made now for what's going on. And you can scale that up to 5,400 ops per second. That's compared to the 1,600 in the public cloud. So we're going to hit a couple other numbers, but you can see the performance is better in this environment. We're going to look at a cost slide in a minute, and I'll show you the costs are roughly the same as well. And maybe more importantly, even than performance, is the standard deviation. The consistency is much better in this environment. That the second number there, the percentages, is the standard deviation, relative standard deviation within a given platform. You can see it's almost 100%. And I'm going to show you a slide in a minute that makes this even more clear. So let's look at another environment, React, another NoSQL database, multiple servers. In this model, the setup was 5 servers, kind of the same sort of setup. Small was about what I described a moment ago. In the public cloud, there's a whole different set of numbers, and I know this is very difficult to read, so I'm going to kind of walk you through it. That top bar is the throughput, measured in gig per second. And you can see a lot of dispersion and a slow trailing off of performance as you scale out. That's the number of operations on the bottom. The bottom 2 sections there show the latency, millisecond latency. Starts at the median level at about 250 milliseconds. You can see the slower ones, though, were experiencing up to 4,000 milliseconds. That's that standard deviation I was talking about. When you look at the bare metal environment, very tight results and steady. As it's scaled up, you don't see any trailing off of performance. And you can see the median to the top, there's still a pretty good spread, 30 millisecond to 100 millisecond, but you're talking 30 milliseconds as compared to on their previous slide, you're talking 250 milliseconds, and it's a triple instead of an order of magnitude bigger. So it's a much tighter space. If we look at the consistency, here's those two consistency graphs, just so you can see the dispersion that I'm talking about in the public cloud. And to even get that level of performance was a very complex environment. I mentioned earlier complexity is something we were going to talk about, but the complexity it takes to scale in a public cloud, to get multiple, to stripe across various storage components is very complex. You end up with lots of things to manage, lots of things to fail, lots of things that can fail. So there's a huge complexity involved in even getting kind of that base level of performance. Again, all of this is not to say that it's bad, merely that there are lots of different ways to go about things. The benefits of the public cloud are instant scale and low cost, low starting cost. But as you begin to map your application into it, there's lots of flavors to think about, right? And just as with wine, they can map wine into the types of food you're eating, different cheeses, white wine with fish, and all those kinds of rules that you learn about. You want to do the same thing with the cloud environment. As you begin to leverage the cloud, think about exactly what you're doing, what your options are, what the different benefits of each of those cloud options are, and how you can leverage them. You can read a lot more about this at our website. There's a bunch of blogs that go through in a lot of detail the performance numbers that I just walked through. There was a presentation yesterday by Mark Jones. I think they catalog all of these. You can go watch on the performance, deep dive on those performance numbers, SoftLayer guy. And we're happy to talk to you always, of course. We've got a big booth in there, so thanks for your time. I appreciate it.
Thank you. Duke Skarda, CTO of SoftLayer, that can clearly now afford to start it.